Welcome to class students. In this class we discuss impact of logic synthesis. A logic synthesis means the high level blocks written in RTL. Using RTL means using data flow and behavioral descriptions. Combining those descriptions we refer it as RTL descriptions. Those high level blocks need to be converted into gates. We have discussed few of the constructs in last class. Today's class we will see function statement. The function statement, the functions synthesize to combinational blocks with one output variable. The output might be scalar or vector. A 4-bit full adder is implemented as a function in the Verilog description below. The most significant bit of the function is used for the carry bit. Function 4:0 full add, so it is returning 5-bit value. A cout and 4-bit sum together 5 bits it is returning. We know that function can return one value. Here you can see inputs are defined. A and B are of size 4-bit, Cin is of size 1-bit. 3 inputs are defined and you are returning full adder, which is including final carry out, sum 4 bits as well as final carry bit. So total 5 bits we are returning. So full adder is defined, function full add is defined as 5-bit. And within the function body we are writing full add is equal to, using arithmetic operators we have implemented the design A plus B plus C in. So it will bit 4 of full add for carry, bits 3:0 for sum. Total altogether 5 bits are computed and they are assigned to full add. So this particular assignment statement will generate a 4-bit ripple carry adder. 4-bit sum along with carry out together it is returned by this function, and this function is synthesized, so it is equivalent to 4-bit ripple carry adder. We will see impact of logic synthesis. Logic synthesis has revolutionized the digital design industry by significantly improving productivity and by reducing design cycle time. Before the days of automated logic synthesis, when designs were converted to gates manually, the design process had the following limitations. For large designs, manual conversion was prone to human error. Small gate missed somewhere could mean redesign the entire blocks. So what we are discussing is, we are comparing here automated design process and the manual process that is done earlier. Logic synthesis. In logic synthesis, the design process had following limitations. When manually the designs were converted to gates, in that case the design process had following limitations. For the first one, for large designs, manual conversion was prone to human error. A small gate missed somewhere could mean redesign of entire blocks. The designer could never be sure that design constraints were going to be met until the gate level implementation was completed and tested. A significant portion of the design cycle was dominated by the time taken to convert high level design into gates. So design cycle means, see, when the specifications are given, and you start developing a code, and then high level blocks to gate level implementation. So the time taken to convert the higher level blocks to gates used to take more time. If the gate level design did not meet requirements, the turnaround time for redesign of blocks was very high. What if scenarios were hard to verify? For example, the designer designed a block in gates that could run at a cycle time of 20 nanosecond. If the designer wanted to find out whether the circuit could be optimized to run faster at 15 nanosecond, the entire block had to be redesigned. Thus, a redesign was needed to verify what if scenarios. Each designer would implement design blocks differently. There was a little consistency in design styles. For large designs, this could mean that smaller blocks were optimized, but the overall design was not optimal. If a bug was found in the final gate level design, this would sometimes require a redesign of thousands of gates. Timing, area and power dissipation in the library cells are fabrication technology specific. Thus, if the company changed the IC fabrication vendor after the gate level design was complete, this would mean a redesign of the entire circuit and a possible change in the design methodology. Design reuse was not possible. Designs were technology specific, hard to port and very difficult to reuse. This is with respect to a manual conversion into gates, which is done earlier. Earlier means when computer aided tools were not available. At that time, these were done manually. Now, for converting, for logic synthesis, converting high level blocks to gates is done by automated tools. We'll see that scenario. Automated logic synthesis tools addressed these problems as follows. High level design is less prone to human error because designs are described at a higher level of abstraction. High level design is done without significant concern about design constraints. Logic synthesis will convert a high level design to a gate level netlist and ensure that all constraints have been met. If not, the designer goes back, modifies the high level design and repeats the process until a gate level netlist that satisfies timing, area and power constraints is obtained. Conversion from high level design to gates is fast. With this improvement, design cycle times are shortened considerably. What took months before can now be done in hours or days. Turnaround time for redesign. Conversion from high level design to gates is fast. With this improvement, design cycle times are shortened considerably. Earlier it was done manually. Now with automated logic synthesis tools, so design time it become fast or it takes less time to complete. What took months before can now be done in hours or days. Turnaround time for redesign of blocks is shorter because changes are required only at register transfer level. Register transfer level means at a higher level where you are writing HDL description at that level. If you change HDL description and again if you synthesize new set of gates based on the logic that you have written, it will be generated. The design is simply resynthesized to obtain the gate level netlist. What if scenarios are easy to verify? The high level description does not change. The designer has merely to change the timing constraint from 20 nanosecond to 15 nanosecond and resynthesize the design to get the new gate level netlist that is optimized to achieve a cycle time of 15 nanosecond. Logic synthesis tools optimize the design as a whole. This removes the problem with varied designer styles for the different blocks in the design and suboptimal designs. If a bug is found in the gate level design, the designer goes back and changes the high level description to eliminate the bug, and then the high level description is again read into the logic synthesis tool to automatically generate new gate level description. Logic synthesis tools allow technology independent design. Okay, here some words we need to understand. Technology independent design. So while writing HDL description or higher level blocks, we don't worry about the target device on which we are going to, or technology or the device on which we are going to dump it. Without bothering which target device we are selecting, we are writing higher level blocks, which we call it as technology independent design. One more term repeatedly you see in your this video, RTL description. RTL description is nothing but an HDL description consisting of data flow and behavioral style of coding together, mixed together. A high level description may be written without the IC fabrication technology in mind. Logic synthesis tools convert the design to gates using cells in the standard cell library provided by an IC fabrication vendor. If the technology changes or the IC fabrication vendor changes, the designer simply use logic synthesis to retarget the design to gates using the standard cell library for the new technology. Design reuse is possible for the technology independent descriptions. For example, if the functionality of the I/O block in a microprocessor does not change, the RTL description of the I/O block can be reused in the design of derivative microprocessors. If the technology changes, the synthesis tool simply maps to the desired technology. In this class, we have seen impact of logic synthesis. We have analyzed manual process as well as automated logic synthesis tools process. What were the problems faced earlier, how it is taken care by automated logic synthesis tool used nowadays. We have also discussed a function statement, how a function statement written in HDL module is converted to hardware or into gates. So in this example, it is converted to a 4-bit ripple parry adder. We'll continue in next class.